All right, let's start. I'm glad you showed up despite the festivities last night. So today we're going to start talking about, this will just be about a half lecture on boundary integral equations. So this will be a very summary presentation. The point is really just to hopefully refresh you of some concepts from boundary integral equations, introduce my notation, and possibly if somebody has not seen this, then hopefully I'll entice you to read more about it. So it's a very interesting topic. So the idea here is, so again, our underlying problem is to address some sort of elliptic linear PDE, such as the Laplace equation, the Helmholtz equations, the equations of linear elasticity, and so on. And the idea here, what we're going to talk about in the morning, is that in some environments it's very advantageous to rewrite the partial differential equation as an integral equation. And this can be particularly advantageous if there is no body load and when the operator A has constant coefficients. So for instance, this equation is an example. So if G is 0, then you'll notice that the input data here is really, if we're in if omega is a three-dimensional domain, then its boundary gamma is a two-dimensional domain. So the input data is two-dimensional. So it sort of makes intuitive sense that you should be able to write an equation that's defined on gamma. And you can. So just to give an example, so let's consider that this is one of the archetypical examples for when boundary integral equations are useful. So we're looking at an external scattering problem. And this slide is a little schizophrenic because the picture sort of indicates electromagnetic scattering, and then the equations are Helmholtz, which is acoustic scattering. Yeah, I didn't know how to draw a submarine, so. In any case, so we'll return to the question of exactly how to rewrite the equations of the partial differential equations as a boundary integral equation. But before we start, let's just review this. So here is the partial differential equation that governs acoustic scattering in the domain exterior to this body. And here is the corresponding integral equation. And the main point here is that the integral equation really only lives on the surface of the scatterer. So let's compare the two approaches. So if you do the PDE formulation, so notice that these are two perfectly valid mathematical formulations of the same underlying physical problem. So the some sort of physics, you cast it as a mathematical equation, and there are two equally valid ways of doing this. And there are several advantages to doing this as an integral equation. And now I'm going to a little bit repeat myself from the discussion of the advantages of looking at solution operators to elliptic PDEs as opposed to the elliptic PDE originally. Precisely because the solution operators are integral operators, and in this case, the underlying equation, the equation we start with, is also an integral equation. So it has a number of advantages. So for instance, in this case, the computational domain is finite as opposed to the infinite domain out here. If you want to solve the PDE numerically, then the typical technique is to enclose this box in some finite domain and impose some sort of artificial boundary conditions, such as perfectly matching layers that mimic the radiation condition at infinity. But of course, at least in my opinion, it's nicer to enforce it exactly, mathematically. Sort of cook it into your mathematical formulation. Of course, the mathematical operator, if you look at the partial differential equation situation, then you have an unbounded operator. If you discretize it faithfully, as we discussed yesterday, you're necessarily going to get a matrix with a very large dynamic range of its singular values or eigenvalues, which leads to ill conditioning. And this can, of course, be handled. It is handled, as a matter of course in daily computations. But it is a complication that you need to deal with. And in some situations, we don't know how to deal with it. In contrast, when you reformulate as an integral equation, you certainly get a bounded operator. It's a smoothing operator. It's oftentimes a second-kind Fredholm operator. So they're very nice mathematically. The main drawback of working with the integral equation is that these are global operators. Every point in the domain talks to every other point. So you end up with dense linear systems. The coefficient matrix in the linear system is dense. And this is something you need to deal with. Of course, in these lectures, our overall objective is to build direct solvers. And the direct solvers are themselves global operators. So if your objective, thank you. Great. So if the objective is to build a direct solver, then there's really a very small additional penalty in starting with a dense linear system. All right, so let's just look at some simple examples of how this can be done. So let's start with the equation I had on the first slide. So this is really the archetypic, it's a very simple example. It's a common thing to look at first. So we look at the Laplace equation, no body load, and then I simply impose the Dirichlet boundary condition to this equation. So we know that the solution operator takes this form. It's some sort of integral against what's called a Green's function. So this function h here, it's not the free space fundamental solution that we talked about extensively in the first lecture. Instead, it's a function that's really genuinely a function of two variables, of x and y. It's not a convolution or anything. So this is called a Green's function. It depends on the domain. For simple domains, you can determine it analytically. So these would be things like a circle in the plane, say a half plane in space, maybe a cylinder. There's a number of simple environments where if you go to a textbook of mathematical physics, preferably an old one, you'll find lots and lots of techniques for solving these things via separation of variables, basically. But more generally, we don't know the Green's function h. So what do we do then? So I alluded to this in the first lecture, that what you can do is you can use various representation theorems. So for instance, you can show that while the exact solution of this equation is given by that equation, you can show that there typically exists a representation of the solution that involves the free space fundamental solution. So there's some map whose kernel is the free space fundamental solution that maps some sort of boundary function to the function you want to compute. Which sort of tells you something about the information content in the equation here. And once you have these types of representations, then you can derive, so now the advantage is that we have a known kernel in this equation. The disadvantage is that now the source distribution sigma that lives on the boundary is an unknown. So this is my new unknown. How do we get an equation for sigma? Well, for this particular representation, so the free space fundamental solution, it's weakly singular. So it's integrable, which is to say that u in this case, the function u, will be continuous across the interface. So you can define this for any x in the plane. It has a continuous limit as you approach the boundary gamma. And of course, you know what u should be on the boundary, simply the Dirichlet data. So you plug in the Dirichlet data and you get this equation for sigma. So now we've derived some benefits. We've reduced the dimensionality of the problem. But actually, this equation, it has improved the conditioning, but it's still an ill-conditioned mathematical equation. So for the Laplace operator, its spectrum goes off to infinity pretty rapidly. But this is what's called a single-layer potential, and its spectrum goes to 0. So in either case, you end up with an ill-conditioned matrix. The decay here tends to be slower, so you've gained something, but we haven't fundamentally changed the situation. But you can actually do better. So what you can do instead is that you can look for a solution in the form of what's called a double-layer potential. So here the idea is this. You have your domain, omega, and we're looking for the solution at some interior point x, and we write it as a linear combination of potentials induced by dipoles on the boundary. So at this point of y on the boundary, we have some dipole moments. So a dipole of strength sigma y in the direction n of y. And then you have some infinitesimal boundary contribution, and you sum them all up. Okay. So that's our new representation. So this might look a little more unpleasant, because now we have a stronger singularity in the kernel, which means that if you view this u of x as a function of x all over the plane, it's an analytic function inside the domain, as long as you're away from the boundary. It's analytic outside. But as you approach the boundary, some funny things happen. So specifically, it's a discontinuous function across this interface. So this looks like it's somewhat unpleasant, but it actually ends up very nice, because you can compute this limit. So if you're in the inside of the domain and you let x approach the boundary, what happens in the limits. So this is a well-defined, this function has a well-defined limit, and it looks like this. So now we put in the Dirichlet data and then the limiting value over here. And now the very nice thing is that we got a little sigma popping out here. So the form of the operator on the left-hand side here is identity plus an integral operator. Under modest smoothness conditions, this can be viewed as a compact operator in the correct function spaces. And then there's a little quirk with this particular equation, that if gamma happens to be smooth, then this kernel is actually a C-infinity function. But that's a little bit of a special case just to this specific situation. All right, so this is what's called a second-kind Fredholm equation, which is a second-kind Fredholm operator. It's a continuum operator, but it's really, among the various classes of continuum operators, it's one of the ones that behave almost like a matrix. It's almost a finite dimensional operator in the sense that all its singular values here will cluster around 1/2. So to finite precision, there's basically finitely many modes that deviate from the identity. And this really simplifies things. You get closed range and, you know, a bunch of nice things follow from this. Okay, so let's just look at the spectra. For instance, so this is from the graph we had earlier in the week. We looked at the Laplace operator on a square. These are its eigenvalues with Dirichlet boundary data. Here are the singular values of a second-kind Fredholm equation of this operator specifically. For some gamma, I think it's the smooth starfish or something like that. And you see here that the singular values just cluster to 1. So it's, I guess I multiplied the equation by 2 or something. So there's really only finitely many mode heres that you need to really worry about numerically. And the upshot of this is that when you apply an iterative solver to this GMRS or something, it will converge extraordinarily rapidly. And so here are actually the condition numbers. And these are numerical condition numbers. I don't know how to determine them mathematically, but in this particular case, because you can discretize integral operators to very high accuracy, you know, it converges very quickly, as you can see here. So this is for the special case we have a smooth kernel, but with some mild modifications, as Alex showed us on Monday, you can get the same thing happening for most weakly singular kernels and a bunch of other ones as well. Okay, so what about Bodyloads? So I mentioned earlier that the integral equation framework, it's particularly nice if you have constant coefficients and Bodyloads, but you can still handle Bodyloads because these are linear equations, right? So we can split this problem into 2 halves. So you can first consider just the Poisson equation, minus Laplace u equal to g. Consider that by itself and just don't worry about the boundary condition for a moment. Then we can certainly solve this equation. So specifically, we know, oh, that should be a g. That's a typo. So we know an analytic solution, for instance, to the Poisson equation, and it's given by simply convolving with the free space Green's fundamental solution. So you get this sort of expression for v. So v now, if I compute minus the Laplace operator of v, I get specifically g modulo the typo, and we find that the top equation is satisfied. So this handles the body load. So then the remainder, so now view the solution u as a superposition of what we call the particular solution v, and then the remainder is what we call the homogeneous term. So the homogeneous term satisfies the Laplace equation with no body load, and then this modified Dirichlet condition. Right. So in principle, this is very easy. If you try to execute this numerically, you find that if you don't care so much for accuracy, then it's very easy. If you want high accuracy in this, then there's quite a lot to think about, because notice here that you're integrating. So the first difficulty is that the kernel is weakly singular, but then the much more hard thing to deal with is that you're executing an integral really over R2, and then you have a discontinuity, because now your body load is supported in your domain, and as you cross this boundary, various unpleasant things happen. So you have to think quite carefully about how to construct quadratures for these equations. And Leslie Greengard's group has done a lot of work in this area. Okay, so just to recap, so in this little presentation, we looked at the Laplace equation. We showed two different boundary integral equation formulations for it. They're both valid. One is much better than the other one. And this is very typical. So one point I wanted to make in this lecture is that if you want to work with integral equation formulations, you have to spend a little bit of time researching which one is the best one. And yeah, so there's usually a choice, and the choices are not equivalent. Okay, so a few quick notes about the Helmholtz equation. So I should mention again that this is a vast subject of study. So I'm just scratching the surface here, just introducing some very basic concepts. So now let's look at the corresponding Helmholtz equation. And we can do the same thing. So we introduce single layer operators, where it's just convolution against the free space fundamental solution, and convolution against really sort of Helmholtz dipole charges on the boundary. So this we call a double layer operator. And you can exactly follow the pattern of the Laplace equation. You can derive the double layer equation. So this is a second-kind-Fredholm equation. It's, but there, something unfortunate happens when you do this for Helmholtz, which is that, so we talked about the fact that this equation is sometimes ill-posed. Specifically, if kappa is an eigenvalue, or if kappa square is an eigenvalue of the Laplace operator, then this equation is ill-conditioned. So the boundary integral equation inherits, of course, any resonances that it must inherit from the physics of the problem. But then there can also be additional artificial resonances. So the boundary integral equation can sometimes be a little worse than the physics really would indicate. This can be dealt with. So what you can do is you can play with looking at linear combinations of the double layer and the single layer potential. If you do this correctly, and if you ever implement this, don't trust this slide, because getting the little factors I quarter and plus minuses and all this stuff is, yeah, you need to look this up. And then when you code it, just do a quick check. And you know, if it's not right, just try a few different possibilities and see if you can get it right. Right. Okay. So for Helmholtz equation, it's basically known how to deal with this. You can go to standard textbooks and look it up. But the more difficult situation is time harmonic Maxwell. In this case, it's less well known how to cast this in boundary integral equation terms. So there are a variety of formulations. Many of them are used commonly in engineering practice. There's some very novel work, very recent work by, for instance, Greengard and Epstein. And there's a lot of work in this area, finding good formulations. So let me just quickly mention that you can do this for a range of different equations. Linear elasticity, for instance, is commonly cast as boundary integral equations. You can do it for Stokes, for very slow fluid flows that are dominated by viscosity. And for each one, there are some peculiarities about the physics and the fundamental solutions and so on. Something that we're going to talk about, let's see, so I want to spend maybe another 10 minutes on boundary integral equations. So we're going to talk about how to integrate, how to discretize these things. And then a major difficulty is that, or the difficulty, I should say, it's certainly manageable, is that the kernel functions tend to be singular. So most quadratures, if you take them out of the box, you won't get very good accuracy. So this is something you certainly need to deal with. If you have corners or edges, then you have to deal with that. It's, there are a number of techniques, but just like with any discretization procedure, this is exactly the same if you're using finite elements or finite differences or spectral methods or whichever discretization technique you use. If you have corners and edges and the functions you want to solve for have some sort of non-smooth behavior here, you have to deal with it one way or another. Right. Okay, so let's talk about discretization of boundary integral equations. There's a number of different ways of doing this. There's, for instance, something called a boundary element method, which is a surface equivalent of finite element methods for PDEs. So I'm instead going to talk about the Nystrom method. And this is, like Alex pointed out, this is, there seems to be some sort of cultural issue here, that in the US, many people work with Nystrom. In Europe, many people work with boundary element methods. Right, so given our geography, we're going to talk about Nystrom. So in any case, so the basic idea here is simple. Of course, the devil is in the details once we start looking at real problems. But the basic idea is simple. So we start by assuming that we have some sort of quadrature for the surface under consideration. So I'm going to write this like this. So given a smooth function phi that lives on the boundary, we need to be able to integrate it somehow. So what we're going to do is that we're going to approximate this integral by looking at pointwise values of the function on the boundary. It's a standard quadrature multiplied by some sort of quadrature weights. So I'm sweeping some stuff under the rug here. So Alex very helpfully laid this out in great detail, that in order to construct this rule, typically what you do is that you look at a parameter map. So in this case, if you have a curve, then you have some sort of parameter space, and then you have a map that takes you from a point in parameter space to a point on the curve. Then you use some sort of classical quadrature rule in parameter space, the trapezoidal rule, composite Gaussian rule, something like this. And that will give you your weights up here. So then you have to worry about things like the speed function, or how do you try to find a reparameterization so that you parameterize by arc length. And there's a bunch of technicalities going into this. But at the end of the day, we end up with some sort of quadrature for functions on the curve, like this. So now Nystrom discretization consists of two parts. First, we collocate this equation. We collocate the continuum equation to the collocation nodes, so to your quadrature nodes. So we enforce that this equation has to be satisfied at the quadrature nodes xi. Then the second part, okay, so this only did half the job because we still here have a continuum integral. So next we're going to plug the quadrature rule in to approximate the integral. And then you end up with a linear system. So notice here, so this is the discretized version of the original equation. Notice that I'm temporarily assuming that the kernel function is smooth. This is extremely untypical. But if it happens to be smooth, then this is what you do. So notice now that the unknowns, the inputs, are the values of the boundary condition at the collocation nodes. And the unknowns, so what we're solving for here is the vector of collocated values of the source function Q, of this charge distribution Q. Right. And here are your matrix elements, basically. There's a number of different underlying rules you can use. You can use the trapezoidal rule. This is particularly convenient for in 2D. If you have a smooth curve in 2D, then this is very nice. More commonly, we use some sort of Gaussian quadratures. So in 2D, you can partition parameter space into panels. On each one, you put down a Gaussian quadrature. This is particularly convenient if you have corners, say, or if you have some local area where the curve behaves more irregularly. So in this case, you probably want to do finer discretization. So also in 3D, you have much more complicated topological possibilities in 3D and ways of constructing surfaces. So in that case, it's sort of easier typically to localize the problem. So if you're given a surface, you typically specify it as some sort of collection of patches parameterized over, say, triangles. And in this case, doing some version of Gaussian quadrature, doing a localized panel quadrature is very convenient. But you can certainly use other quadratures as well. So right now, for various reasons, I'm looking at rules that happen to have a collocation point right at the end points of the intervals. So then you can use Curtis-Clenshaw quadrature, for instance. So there's a range of different quadratures you can use here. The discussion is basically agnostic to which one you use. Okay, so now suppose that K has some sort of singularity. Initially assume that it's a weak singularity so that we can just integrate through it in principle.
Yeah. Can you go back to the previous slide? I'm not that familiar with Per-Gunnar, but it seemed like its distinguishing feature was looked at the endpoints. How does it contrast with like a Gauss-Lovato kind of rule?
Right, so, so the way I think of quadratures is you start by specifying some interpolation points. So you have some underlying set of functions, typically polynomials. Sometimes things like Fourier functions. You want to integrate these exactly. So the first thing you do is that you specify a good set of interpolation nodes for the set of functions. And if you look at an interval, and your set of functions that you want to integrate exactly are the first few polynomials, then putting down the Gauss-Legendre nodes is they're a good set of interpolation nodes for interpolating polynomials. And then once you've specified the nodes, the quadrature weights are uniquely specified by the fact that they have to integrate exactly the function set. All right, so Curtis-Clenshaw, it works exactly the same, just that now we use a different set of, so there are several different good set of interpolation nodes for polynomials. So Curtis-Clenshaw is based on the Chebyshev nodes on the interval, which are easier to compute, and they include the endpoints. So now Gaussian quadrature has an advantage in that it's really the most optimized quadrature. So if you specify the interpolation nodes first, then typically you get convergence h to the p with p points. Yes. So in Gaussian, when you design Gaussian quadratures, you have 2p free variables that you can optimize. You can optimize both the locations of the nodes and the weights. And this allows you to get much higher accuracy. So, so in some sense, Gaussian quadrature is, if you're really primarily interested in integrating, then it's the optimal choice. But in practice, Curtis-Clenshaw works very well. You get a slightly lower accuracy in practice, but it's not the case that you get vastly lower. Anything else? No. Okay, so now let's return to the case where the kernel has some sort of singularity. So we start by doing exactly the same thing. We collocate at the quadrature nodes. But now the difficulty is designing a matrix such that you can approximate this interval accurately. And this is where things get hairy. Alex did an excellent job of covering a wide range of techniques for doing this very quickly. I'm not going to try to emulate that. So let me just touch on what we're doing conceptually. So in principle, so what we're using in designing these rules is that the function q tends to be smooth. If the underlying contour is smooth, then the unknown q will be smooth, which means that if you specify q on the collocation nodes, so in the end, I want a linear system whose unknowns is a vector of the q values at the collocation nodes. Now, if I know these values, then I can certainly interpolate q to get a continuum function. So then the question is just, how do I evaluate integrals against this singular kernel for this specified function? So I hope that at least mathematically you sort of see how this works. Specifically, what's the objective? Then the way we execute, there's a number of ways of doing this. Here I'm just showing a quick cartoon to remind you of how it works. We use a Gaussian base quadrature. So we put panels onto the contour. And then you have to do this type of thing that we talked about when we looked at the FMM, that you separate, so you have some panel or self-interaction. So this is the panel to which the point xi belongs. Then you have two panels that are reasonably near. And the point now is that the integrand behaves a little bit unpleasantly in these intervals. So here you basically have to do something. You have to do something It's modestly expensive in terms of flops, but it's a completely local operation. So it's very feasible to do this. And then the main point here being that in the far field, you're good. The kernel is smooth on the blue nodes. So there you just plug in your standard quadrature weights. And what you end up with once you discretize is you have some sort of far field discretization. So in the vast majority of the nodes, in all these blue nodes, the matrix is given just by this simple analytic expression. It's really just collocating the kernel function and multiplying by the quadrature weights. And then you have to numerically construct the near field interactions, basically. Right, let me quickly mention that sometimes it's advantageous to re-weight things. So I mentioned what happens if you have a corner. So something you can do if you have a corner, now the unknown sigma will blow up, typically near the corner. And then a common technique for dealing with this is to locally refine. So you put smaller and smaller panels as you approach the corner so that you can properly resolve the integral. Now, you have to think a little bit what happens to the linear system here, because it could easily be that you need maybe 200 points to discretize out here and then 2,000 points to discretize up there. And now you don't want to direct your linear solver to put all its energies into just satisfying the equations over here. So you want to give every panel weight that's proportionate to how much it actually contributes to the original equation. And there's a variety of ways of doing this. Something that James Bremer has been pushing that I think is particularly nice is to scale your vectors by the roots of the quadrature weights. Because then what happens is that the L2 norm of the vector turns into a good approximation of the L2 norm of the corresponding continuum function. Okay? When you do this, then the matrix elements looks like this. We used to just have multiplication by Wj by itself. Now we instead have multiplication by both Wi and Wj. But from the algorithmic point of view, these things, from the point of view of designing solvers, it really doesn't matter because these are really just diagonal modifications to the kernel matrix. The trickiness is handling the kernel in the middle. And then these two are just diagonal corrections. So, it's a very convenient thing to do. And it does not really cause difficulties. Right. So I think I've already touched on most of this. Are there any questions? I'm next going to proceed to talk about direct solvers. Any questions on boundary integral equations or Nystrom discretization? No. Okay.
But if you have several corners, you still become ended.
Oh, yeah. Yes, no, the more... So the situation where it doesn't matter how you weight is if you have a contour that's sort of evenly difficult. So that evenly spreading the discretization nodes works fine. The more you have these situations where you have clustering of discretization nodes in certain regions, the more important it becomes to think about this issue of weight.
What if the equation is nonlinear? Like, for example, a wave equation with a constant velocity?
Right. So in that case, we can use so the techniques for this entire week. They're really targeted at linear problems. So when you solve nonlinear equations, sometimes you need to solve linearized equations. If you time step Navier-Stokes, you need to solve some modified Helmholtz equation, typically in every time step. Some of these techniques are very helpful in those situations, but yeah, they don't address the fundamental issue of nonlinear equations. All right, let's move on to direct solvers. So in this lecture, And tomorrow as well, I'm going to draw on a bunch of earlier work. So the basic idea that you can do fast operator algebra for a range of operators that arise in classical harmonic analysis, in mathematical physics, I like to intellectually trace this back to work by Belkin, Kaufman, and Rokhlin about representing these types of operators in wavelet spaces and sort of showing that in principle you can do a lot of interesting things with them. The specific algorithm that I'm going to describe it's a descendant of work by Rokhlin and Starr from about 20 years ago. And then I also would like to mention these H-matrix methods by Hackbusch, which is a generalization of the fast multiple method. Then the objective here was to permit you to perform other types of matrix algebra. Like we talked about in this lecture on structured matrix algebra, once you generalize things a little bit, it becomes feasible to do things like matrix-matrix multiply, matrix inversion, LU factorization, and so on. And in Hackbusch's group, they did a lot of work here. They identified a class of matrices for which this is possible and presented explicit algorithms for how to do it, which have complexity n times some power of log n. So what I'm viewing sort of as my main research mission the last 10 years or something has been to really design algorithms that have very high practical efficiency, that does the same thing. So I want to design direct solvers that should have at least comparable performance to iterative solvers in environments where iterative solvers do well, and then hopefully do even better in other environments. Right. And I'll return to related work a little bit at the end of this lecture. So the objective here is really to design direct solvers for solving boundary integral equations. We're going to use, throughout going to rely on Nystrom discretization. That should be lecture 8. So recall we discretize, we get a dense matrix, and remember that the vast majority of the entries of A take this very simple form. So this is not true for near interactions. The elements that corresponds to points xi and xj that are close in physical space, you have to do something different. But for the vast majority of elements, this is what it looks like. Okay, so the standard approach here is to use something like GMRS, or conjugate gradients, an iterative solver, to solve this discretized system. Because it's a dense matrix, you really don't want to use classical Gaussian elimination on it. And when you do that, you need some method for accelerating the matrix vector multiply, for instance, the fast multiple method. And oftentimes, if you have a second-kind Fredholm formulation, you can get very rapid convergence in the iterative solver, and you get O of n complexity. So the idea in designing direct solvers, it's one, to deal with situations where it's hard to get good convergence in the iterative solver. And the other one is another motivation is to handle situations where you need to solve a sequence of these equations. So for instance, the scattering problem that I looked at early on, you have a scattering wave coming in, hitting some scatterer, and then you want to determine the outgoing wave. So typically, for this situation, you're not interested in solving it just for a single incoming wave. You really want what's called a scattering matrix. So you want to determine the response to basically incoming waves from all sorts of directions. So in this case, direct solvers are very competitive. And the main thing we're going to use the only thing we're going to use in these lectures is rank structures. So the off-diagonal blocks of this coefficient matrix tend to have low rank. All right, so let's recall, we've touched upon this a couple times, but all of these methods are based on some sort of hierarchical partitioning of the domain in physical space. So suppose this is our contour. We let the entire contour denote the root of the tree. So this is what I denote gamma 1. I split it in two halves, gamma 2 and gamma 3. And then I just continue going down recursively in the tree. So this half, gamma 2 gets split into gamma 4 and gamma 5, and so on. We've seen figures like this many times. So what this corresponds to is some partitioning of the index vector, like this. And for a simple contour in space, it will look just like this. You get contiguous pieces of the index vector. But notice that more generally, if you have some complicated geometry, say a whole collection of small contours in the plane, you have a contour that doubles back. So if you have some geometry like this, or if you have something that doubles back on itself, in this case, you can't really set things up so that distance in index space corresponds to distance in physical space. So it's important to remember that typically this partitioning is always based on physical space, and sometimes that's very different from index space. Okay, so let's, before we start, just look at some numerical examples. So we, again, take this simple contour. It's a Laplace Dirichlet problem, discretized with Cohn-Rokhlin quadrature. So here I sort of artificially do some combined field Laplace kernel, just to take something that's reasonably representative. So this is what the ranks look like. So in this case, I didn't want to, so the standard formulation here is the double A kernel, but it's cheating. The ranks for that one are very low, but it's an abnormal case. So, right. So let's, so we discretize this equation. You end up with a matrix A. In this case, it's a size 400 by 400. And now I'm using this very simple tessellation that we covered in lecture 3. And now let's look at the numerical ranks. So this is to high accuracy. This is 10 correct digits. And then the off-diagonal block here, so this is a block of size 200 by 200. Its rank is 50. This is what the singular values look like. And it's really a textbook example of exponential decay, of numerically observing exponential decay. This line is completely straight. And notice that this is reasonably honest. We have a singular kernel, there's quadrature corrections, and everything. And the point is that as you increase n, the slope of this curve might shift just the tiniest bit, but it's really largely independent of the overall size of the problem. Okay, now let's look at Helmholtz. So again, a combined field integral equation. So this is for small wave numbers. So this guy is about a little over 1 wavelength across. And let me mention that I put all these, again, these codes, I believe, are on the website. So you can play with this yourselves and determine the ranks for various parameters. So now the rank is basically the same. This is complex valued, so in some sense there's more information, but in a complex factorization, the rank here is 48. Very similar to the Laplace case. This is how the singular values decay. And now you probably know what the next slide is going to be. Now I'm going to crank up the wave number, look at a smaller wavelength. So this is what we always do to make things harder. So now let's look at a domain that's 30 wavelengths across. So this is really quite under-resolved. I don't really accurately resolve this, but as far as the ranks go, the story is basically true. So now the rank went up a lot. It went from 40s up to 87. And we have this very typical picture of the ranks. So we have basically no decay for a long time. Then once you resolve the geometry up to the precision specified by the wavelength. So recall here, the wavelength is 30. So now we're looking at 1/4 of the coefficient matrix. So 823. So this is the geometry. The discretization looks like this. So 823 is the matrix that maps you from one half to the other. And now this distance is 29 wavelengths. And look at where the point of decay starts. So it's roughly at 60 wavelengths. So I'm not saying it always works out this exactly, but you really compress down to the Nyquist frequency, more or less, of the physics. And then after that, it turns into start looking like a Laplace problem. Then you have exponential decay. Okay, so you can certainly design direct solvers based on this, what I call S matrices, but it's not very efficient. It's actually quite hard to numerically compress these big blocks. So we're going to do something quite different. So what we're going to do instead, we're going to use this, this format that we've sort of hinted at several times during the week. Now we're going to do it in detail. I call it hierarchically block separable. It's essentially indistinguishable from what oftentimes in the literature is referred to as hierarchically semi-separable. But I think this term is not, it's slightly misleading. So I prefer HBS. But HSS is a very common term in the literature. So the idea is, so it's a hierarchical factorization. I'm going to start by looking at the non-hierarchical scheme. So now we're going to follow exactly the same steps, right? Roughly the same step as we did when we presented the fast multiple method. That first we looked at a single level scheme. That if you're given your domain and a bunch of source locations, you can just partition it into a bunch of equispaced boxes and then design not really a linear complexity algorithm, but an accelerated algorithm that's based on compressing interactions between these boxes. And then we went to multi-level. So we're going to do the same thing here. We start with a single level scheme, and then once we feel comfortable with that, we'll move to a multi-level. So I'm going to say that the matrix is in a block separable format. If you tessellate it like this, so we just split it into blocks. These are basically equisized. And then each one of the off-diagonal blocks individually admits a factorization of this type. So each off-diagonal block here has rank at most k, numerical rank. And of course here, the implicit assumption is that the rank is substantially smaller than the block size. Otherwise, this would be pointless. Okay, but notice that there's a little bit more. There was something I didn't say. So I'm going to enforce that I can use the same basis matrices. So the matrix UI spans the columns of the blocks of the block Aij. But I enforce that I have to be able to use the same block to span the columns of all the blocks in the same row. Yeah. So here's the off-diagonal blocks A1, 2. So now I'm saying that there must exist a thin matrix U1. So this has only k columns. And U1 has to serve as a basis matrix for all the off-diagonal blocks in this row. Okay? So if we compare this to the situation for back when we were looking at what I call S matrices, U1 only had to span the columns of this block. So in effect, in this representation, the ranks are going to be higher, right? Because I have to determine U1 numerically, I at least conceptually have to compress this entire block. Like this. I apologize. I switched notation on the board. Let me fix that. Like this. Because recall what's happening here. We start with, so this is because of my ordering of the tree. So the tree is ordered like this. like this. So at the level where I have a 4x4 matrix, the blocks are indexed using the numbers 4, 5, 6, 7. Right. So I just try to keep notation consistent. Right. So this is what it looks like on the next row, of course. So U5 has to span all the columns in this block, and so on. Right. So what this means is that so the advantage of using the same matrix U4 to span all these off-diagonal blocks is that now I can very conveniently factor A. So I can write A as one block that's block diagonal with all the U basis matrices on the diagonal. And then on the other side, I have a block diagonal matrix with all the V matrices turned over 90 degrees. And then in between here, I have the interactions between the off-diagonal blocks in compressed form. So here we have A45, for instance, compressed, this guy. So that represents then so now this is gamma 4. Here I have gamma 5. So A45 maps like this. And A45 is a big matrix. But if I express the interaction through these basis matrices, then it's small. So the compressed interaction is A45 tilde. Okay. Then, of course, self-interactions I should not be able to compress, really. That a block's interaction with itself is complicated. It's not a low-rank situation. So then I have this remainder term, which are the self-interactions of the blocks. Now, right, so now remember a few lectures ago, we introduced the Woodbury formula, that if you have a situation where there's a matrix that you can easily invert, and then you add a low-rank correction to it, then you can efficiently compute the inverse of that matrix. So down here is classical Woodbury formula. So here's D, which is easy to invert. Then the inverse is the inverse of D plus a low-rank correction. So observe here that the inner factor here is much smaller. If we apply that to the block-separable matrix format, it looks like this. So we start with a matrix A. We write it as a block diagonal thing that's easy to invert, and then a low-rank correction. The rank is not that low, but it's lower than the size of the matrix. So then we write the inverse like this. Observe here that now we had a little bit of fill-in. The diagonal blocks in the middle here got filled with something. But let me give you a little flash ahead. So the color coding here, I'm going to use a key aspect of getting efficiency here, is that we're going to use interpolative decompositions, which means that the U's and the V's contain a K by K identity matrix. And the A tilde is really, each block in A tilde is a subset of A. It's a submatrix of the corresponding block of A. Which means that A tilde here, I don't need to really compute them. I know what they are implicitly. I have index vectors that just point to them. So I don't need to compute them. But what I do need to compute are these gray blocks. So what's in the gray blocks? Well, let's see, where are we? D hat. It's these guys. All right. So let's see if we can prove this. So of course, we know the Woodbury formula. You can just apply Woodbury and then massage things a little bit, and it will pop out. But let's prove it. So this is something that Leslie brought to my attention. It's a very nice proof of this statement. And it looks like this. Okay, so here's the original system that we want to solve. So here's the coefficient matrix. The unknowns are the sources Q, and we're given the incoming potentials, if you like, or some external potential, I should say, F's. Now, what I'm going to do is I'm going to introduce reduced variables. And we're going to talk more about the physical meaning of these reduced variables tomorrow. But they're really compact representations of the sources. So there's some sort of analog of the outgoing expansion in the fast multipole method of multipole expansions, if you like. But it's a little bit different because what's going to happen is that, for instance, Q4 hat is going to be a compressed representation of the sources on this part of the contour. And it has to be valid everywhere else on the contour. It has to be valid here, like right next to it. So it's a little bit different than the fast multipole method, but it's conceptually similar. Okay, so if we introduce these extra variables, then we can sort of roll out this system. So we write, so it's the same system, but now we write it in terms of both the long variables and the short variables, the original variables and the compressed variables. And then the bottom here is really just the relationship between the compressed variables and the long ones. Right. Now let's form a Schur complement. So I want to eliminate the long variables. If I do one step of block Gaussian elimination here to eliminate the long variables, I get this result. Okay, at this point it's looking a little messy. Why on earth would I want to do this? But if you look at it a little bit longer, you'll see that there's a lot of structure in this mess up here. So all these factors that I now highlighted in red, in one row they're all the same. So we have this factor V4 star times A tilde. That should not have a tilde on it. That's a typo. A44 inverse U4. It occurs in each one of these off-diagonal blocks. So it's the same matrix. So now let's call that something. Let's introduce a name for that. So I call that AII tilde temporarily, and I multiply, or that's the inverse, so I multiply this row by that, and then I end up with this simplified system. Now notice something very important, that once I use the interpolative decomposition, the off-diagonal blocks here are just submatrices of the original corresponding block. All right, so let's see what we've done at this point. So before compression, we had a block system with a matrix looking like this. So the block size is big. After compression, we have a coefficient matrix with the same block structure, but with smaller blocks. So what do we need to do to go from here to here? Well, if we use an interpolative decomposition, all we need to do is that we need to compute the basis matrices ui and vi, which includes, of course, identifying the skeleton vectors that tell you which are the spanning rows and the spanning columns. We need to compute the new diagonal matrices, and then we need to compute the new loads. And that's what we need to do to construct the reduced system. Then the gain here, how much do you gain? Well, if we then use Gaussian elimination to solve this smaller system, it has cubic cost. So we've reduced, so if block size here is n and block size here is k, then we've reduced the size of the system by a factor k over n. And then because of the cubic scaling, we made a gain of k over n cubed, which is good, but it's not, it's not a fast algorithm. So maybe this is a good moment to take a break, and then after the break, at 10:30, we'll talk about how to get linear complexity out of this. All right.